Good evening, everyone. Thank you for joining us for the Caltech Astronomy Stargazing Lecture. My name is Dr. Cameron Hummels. I'm a research scientist here who organizes these events, and we have a wonderful evening for you planned tonight. I'll just go through very quickly what our schedule is before I introduce our speaker. So I've got like a couple minutes of announcements. I'll introduce our speaker. He's going to talk for roughly 30 minutes, all about the formation of our own solar system and how that compares with what we know about other planetary systems and stellar systems that we've detected and observed using telescopes. Like I said, that'll be about 30 minutes, and then we'll have a brief Q&A with all of you fine people. And then it'll be the opportunity for you, if you want to stick around in here, we'll have a Q&A panel going for another hour after that, composed of our speaker, myself, and two other members of the department who work on various different types of astronomy and physics topics. So you can ask us questions related to the content of the presentation, but you could also ask us questions about black holes or the formation of the universe or other things that might be, keeping you up at night that you want to talk to a scientist about. But at the same time as our Q&A panel in here, we currently have telescopes that are being set up outside just behind this building. And there will be 3 telescopes set up on those athletic fields pointed at different objects in the sky with astronomers next to them operating the telescopes. And what you can do is until basically 9:45, you can go out, look at the telescopes, come back in, ask questions, or go home, or do whatever you want. So those will be operating. And tonight, we don't have a lot of planetary objects in the sky, just because they're all on the other side of the sun right now. But what we do have tonight are probably some deep sky objects like the Ring Nebula, the Hercules cluster, maybe a galaxy, something like that. These events take place once a month on a Friday night. Our next one will be, I think we have 2 next month, actually. Next month on August 15th, we're going to have a Spanish language stargazing lecture that's all about black holes. So if you are a Spanish speaker, I encourage you to attend. If you're not, maybe you can learn Spanish in the next month and join us. It will only be in Spanish. It won't be in English, but we'll have that. We'll also have a panel of Spanish-speaking astronomers to answer questions in Spanish, and we'll have the telescopes as well. So that'll happen on the 15th. And then on August 22nd, I'm still looking for a presenter, but everybody's on vacation. I'm still looking for somebody to give a presentation on the 22nd, and I don't yet know the details of that. But as soon as I have a lecture and a presentation topic, I will let you guys know, and I will put it up on our social media, our website, the Caltech calendar, YouTube, all the places that you may have found out about this particular event. I understand this was also covered in Pasadena Now, so maybe some of you raise your hand if you came because you read about this in the newspaper. Nobody. Okay, 2 people. 2 people. 2 people. 2 people read the newspaper. Okay. So that'll happen next month. And in addition to this series of events, we have an informal kind of sister series to these events called Astronomy on Tap. These take place in Old Town Pasadena on one Monday night a month. It's at a bar restaurant, but it is all ages. It's the Doghouse Beer Garden. It's an outdoor space just off of Colorado, and it opens out into a big alleyway, and you can sit there and have a drink if you're of age, or have a burger or whatever. You don't have to buy anything. You can just go for the science. We have 2 15 to 20-minute science presentations, again, like what we're hearing about tonight, at a public level so that anybody who's interested can follow along. And then we have astronomy-themed pub trivia. We have a telescope set up. It's quite fun. Our next one of those will be in a week and a half on Monday, August 4th. I just announced it today. There's a poster in the hallway about it. But if you look, again, at our YouTube or our website or social media, you'll be able to find out about that. The 2 presentations, one will be on supernova, exploding stars, massive stars. When they reach the ends of their life, they explode. And the other will be on a NASA mission called Dragonfly that's going to the moon Titan, the largest moon in the solar system. It orbits around Saturn, and we're sending a NASA mission there composed of a helicopter with 8 rotors that's going to fly around in the atmosphere and take pictures and all sorts of things. So one of the scientists involved in that project is going to talk all about that project, which is super cool. Other announcements. Right now we're live streaming this on YouTube. Hi, YouTube audience. If you come out of this and you want to see more, we have recordings of all of our past stargazing lectures and many of our astronomy on taps on our YouTube channel. So check it out. Just look up Caltech Astro on YouTube and you can find a huge amount of astronomical and space content. In September, there will be 2 special events occurring. We are partnering with 2 national parks to help put on dark sky festivals. One is the Sequoia National Park, just a few hours north of here, the big trees, the mountains. So they have their dark sky festival. It's the 2nd weekend in September. It'll take place from Friday through like Thursday night through Saturday, I believe. We're going to have some members of the department who are coming up and giving public science presentations at that. But of course, the real draw for a dark sky festival is the dark sky. So there will be many, many telescopes available. You have to get into the park, so you either show your parks pass or pay for entry to the park. But once you're into the park, the entire event is free, and it should be really cool. We've helped out at that at the last few years, and it's been super fun. The next weekend, the 3rd weekend in September, we'll be helping out with the Great Basin National Park Dark Sky Festival. That's a little bit farther away. It's about an 8-hour drive from here. It's in central Nevada, but do you know of anything else in central Nevada? No, because it's very dark skies. There aren't a lot of cities. There aren't a lot of lights to pollute the sky and the light pollution. It's one of the darkest national parks. It and Big Bend are the 2 darkest national parks in the lower 48 states. So extremely dark skies, great views of the sky when you don't have lights polluting like we have here in LA metropolitan area or other big cities. You could just look up and see the Milky Way. Pretty awesome. So join us for that. We're going to host a couple of Astronomy on Taps there and help with the telescope. So it should be fun. I think those are most of my announcements. My final announcement has to do with these events. So all of these events, the science that we discuss is science that is paid for largely by the federal government through the National Science Foundation, through NASA, through the Department of Energy. And we as scientists are extremely grateful for the funding that's provided by you, the taxpayers. In fact, much of the reason for these events is to try and share the insights that we gain from the science that we do that's ultimately paid for by the taxpayer. So thank you very much for that. And I'm not going to get political here, but I just want people to know that in the budget that has not yet passed, in fact, the House just went on vacation for a month, but when they come back, they will be discussing the budget. The president's proposed budget cuts funding for science by 50%, basically, through NASA, through the National Science Foundation, through NIH, through various different sources. This is the biggest cut that there will have been to science in the history of this country, and it will be really devastating to American science, both for the people who practice it, as well as just the science that would occur. These events probably will stop happening because I probably won't have a job, but more importantly, the science that we talk about at these events will stop happening in the United States if this budget goes through as is. So if you feel strongly about this, I encourage you to reach out to your representatives and express that you do support science and the federal support of science. End soapbox. Okay, so our speaker for tonight was originally born in Brazil and partially raised in Brazil, partially raised in Mississippi and Maryland before finally settling. He did his undergraduate studies in physics at Rice University in Houston, and then joined the department here as a PhD student in astronomy and physics, and is defending this spring. When is your defense date? In 3 weeks, he will defend his PhD, and this fall he is going to. Yeah, exactly. It's very exciting. So he'll defend in 3 weeks, and shortly thereafter, he'll begin a postdoctoral research position at Harvard, which you may have heard of. And I should also note, I'll get into his academics in one moment, but in addition to his science, he's extremely fast at running. He won the Pasadena half marathon last year with a half marathon time. Yeah, I know. With a half marathon time of 1 hour, 11 minutes. So that's like a 5:30-minute mile pace for 13 miles. He has a 15-minute 5K, and he got 12th in the LA marathon. He got 12th in the LA marathon with a 2:28. So he's a really fast guy. It's a really fast guy. But that's not why we're here to hear from him tonight. We're hearing about solar system, how to build a solar system. So much of his research, he's been doing an amazing amount of research around the formation of planetary systems and the formation of star systems that aren't our own. And a lot of what we understand about these systems can be applied to what we think happened in our own solar system, even though we weren't around, 4.5 billion years ago to watch it unfold. And he's going to be talking about some of that tonight. So please welcome Adolfo Carvalho.
Thank you, Cameron, for that kind introduction. Welcome, everyone. So today, as my slide indicates, and you might have seen the abstract, I'll be talking to you about how we build a solar system. And I'll start out with the story of our own solar system, and then I'll expand a little bit more broadly to all of the other planetary systems that we've discovered so far around other stars that are not, that are not our own sun. So as indicated in my title slide here, we're going to need a lot of dust. That's that little guy there. We're going to need a little bit of math, but I won't actually put equations on the slides, don't worry. We're going to need some conservation of angular momentum, and I'll talk about what that is to sort of set the stage. And we're going to need a lot of luck. But let's get into it. So beginning with the picture of the solar system. Oh, sorry, too many. So let's begin with a family portrait of our solar system. These are images of the planets, many of which I'm sure you've seen before. And they're captured by a variety of telescopes in different wavelengths, and some of them from around Earth, some of them from actually visiting those planets themselves. Our main 8 planets we're going to be concerned with are going to be Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We also have a population of dwarf planets that I've included in this sort of corner here. And these are Ceres, Pluto, Eris, Haumea, and Makemake. These are I'll talk about them as sort of the leftovers of the planet formation process. To get a picture, so this is a nice family portrait. We have some stunning images, but it doesn't really give you a sense of how these planets relate to each other. So let's start thinking about them a little bit more broadly, beginning with how their sizes appear to us. So we have, when you look at the relative sizes of the planets here, and this is just showing them to size scale. I'll get to distance scale in a second, but the distances between them are not represented in this plot accurately. We have the sun, which is huge, of course. We have 4 tiny planets and 4 much larger planets. The smaller planets are the terrestrial planets, those first 4 that I listed before: Mercury, Venus, Earth, and Mars. And then we have 4 giant planets. That's Jupiter, Saturn, Uranus, and Neptune. The giant planets are also split into their own sort of populations, being the gas giants of Jupiter and Saturn, and the so-called ice giants of Uranus and Neptune, which are much less massive. Zooming out a little bit to look at how things are distributed in the solar system, we have, I'm going to show, the plot that I'm showing here, or the illustration I'm showing here, is in units called astronomical units. These are the distance between Earth and the sun. That distance is about 93 million miles, or about 150 million kilometers. And that distance lets us measure things on solar system scales, and so I'll be using those units a lot throughout this talk. In these units, we have Mercury at about 0.3 to 0.4 AU, Venus at about 0.7, Earth, of course, at 1, Mars is at about 1.5. Then we have a break. We have the asteroid belt, which I won't discuss very much in this talk, but it's there, from about 2 to 4 AU. We have then Jupiter at 5, Saturn at 10, Uranus at 20, Neptune at 30. After that, we get into the Kuiper belt. This is a belt of planetesimals from about 30 to 50 astronomical units in our solar system. And it really marks the kind of outer boundary of where a lot of the planet formation action happened in our solar system. And that's where Pluto lives. That's where the Kuiper belt objects live, and these other dwarf planets. In this image, I have a couple of other things I'm going to talk about, but they won't be what I'll be focusing on in this talk. So just to orient people from other things they might have heard of in the solar system, we have the heliopause and this termination shock. Basically, what those are where the solar wind is protecting us from the interstellar radiation around us. So The solar wind is able to, its pressure creates this bubble that has a radius of about 100 AU. Beyond that, and that's sort of in this plot, sort of for the time I took it at, which was probably like 10-ish years ago that it was made, it had Voyager. That was about the location of Voyager. It hasn't gone much beyond that, but Voyager is in interstellar space. Beyond that, we have the Oort cloud, which are a collection of bodies that, and here you can see the number starts to get really large. Now we're at about 1,000 to 100,000 AU. And the Oort cloud is just this sort of sphere of bodies around the solar system that are inside the sun's gravitational influence. But they're not really things that interact very often with us, except for maybe if they get kicked in by some dynamical interaction between some collision between objects in that Oort cloud. And then the final things here are the next stars over. You notice that the exterior part of the Oort cloud is about 1/3 of the way to Alpha Centauri. And so that's the sun's gravitational sphere is gravitational influence is quite large in these scales. So when we're talking about planet formation, I'm going to really just talk about broad strokes, and I'm going to focus on what really set the stage early on. So I'm not going to talk about Earth's atmosphere. I'm not going to talk about those specific details of how we got there. I'm going to talk about how we get a solar system architecture like ours. So what are the main things in our solar system? We have 4 giant planets, like I said before. 2 of them are gas giants. 2 of them are ice giants. We have 4 terrestrial planets. We have 4 terrestrial planets. Those are the smaller ones. Really, 2 of them are about Earth size. That's Earth and Venus. The other 2 were sort of leftover material. And I hope no one gets too mad at me for saying this. But Mercury is 1/20th the mass of Earth. Mars is 1/10th the mass of Earth. In the grand picture of how you build these planetary systems and where all the mass has to come from, it's not that hard to kind of come up with bodies that are about that big. In fact, a lot of models sort of overproduce them or make them a little too big. So we're not going to concern ourselves too much with how we exactly form Mars and Mercury. There's a lot of questions in our own solar systems for that. But mainly we're interested in the fact that we have these kind of terrestrial bodies. And then we have this Kuiper belt of other leftovers that are out in the solar system that are usually bodies that are called planetesimals. The first stage of our journey here is going to really be focused on the first 1,000,000 years. So our solar system formed 4.567 billion years ago. We do know it to that level of precision from radioisotope dating of meteorites that come to Earth. And these meteorites show us some of the first solids that formed in the solar system, and that's what tells us when the solar system itself might have formed. So 4.567 plus minus 0.001 billion years. That's essentially plus minus 1,000,000 years. That's when all this action is, the first formation of the sun and the solar system is happening. Okay, so we get the sun. This recent really exciting result actually came out only a couple of weeks ago in a nearby young star. And I'll talk a little bit more about what these kinds of pictures look like. You have a similar picture that you might have been handed earlier today. But this is a young system, just like our solar system, where astronomers have actually found evidence of those first solids forming. So we actually know this happens and how it may happen and what it may look like, even all these years later. The next thing is that dust is going to clump up. It's going to start at micrometer sizes, so 1/1,000,000th of a meter. It's going to then clump up into millimeter size objects and pebbles and rocks. And then those are going to come together to form what we call planetesimals, things the size of asteroids, comets, and like Pluto. But let's move forward now. The sun started out as what we call a giant molecular cloud. It started in a giant molecular cloud. These are huge, huge clouds of gas and dust in space. This is about, if you remember from the plot, the Oort cloud extended to about 100,000 AU. This is a scale bar showing about 90,000 AU for the giant molecular cloud called L1551 in, they're not very inspired names, in the Taurus constellation. This is a really stunning image taken by an astrophotographer. And before I get into exactly how we form the sun, I want to take a brief interlude to just remind people about the force of gravity. And a lot of you, I'm sure, have heard of it. Gravity is what keeps us on Earth, right? That's what prevents us from floating out into space. Something people might not think about as often is the fact that we are pulling on the Earth just as strongly as Earth pulls on us. It's an equal and opposite reaction. And that's because gravity is the force that attracts objects that have mass to other objects that have mass. So if you are matter and you have mass, then you attract other matter via the force of gravity. What that means is that clouds in space, these big gas and dust clouds, are going to be attracted to sort of themselves. They're going to pull their own material in. They're going to want to contract and come together. And what's preventing that is the random motions of the gas and dust in the cloud itself. It sort of creates an opposite pressure that's balancing out the gravity. And that holds pretty well for a while. But gravity is pretty relentless, and it'll continue to pull the material in. And you get these little clumps locally in the cloud. And those clumps will eventually reach a critical density. And when they hit that critical density, there's no stopping it. And they're going to collapse. And you'll form first this kind of big, dense, spherical cloud of material. And then that material will settle into a disk. And so you get this little picture of the disk. Again, this is sort of a very cartoony version of the picture that you might have gotten before. And the reason that this forms into a disk is because of a concept called conservation of angular momentum. We can't really tell it very easily just from looking at these clouds. In fact, in the images, of course, you can't see it at all. But the clouds are rotating. They're rotating really slowly, but the clouds are enormous. And when they collapse into a star, they go from very big to very small. And when you have rotation and you go from big to small, you tend to want to rotate faster. And that accelerated rotation is going to provide extra support against gravity. It'll push things outward. It's this sort of centrifugal force that people might be familiar with, right? And that means that if you're very close to what's called the rotation axis, basically the center around which the cloud is rotating, if you're close to that, you don't have very much angular momentum. So you kind of just fall right into the star, and that's fine. And that's why material that's above the star sort of just goes to the center. But material that's far away is going to struggle to come all the way in. So it's going to settle along this plane, and that's going to form a disk. Here's a simulation. Sorry, I missed that slide. So you might be familiar with the, I forgot to include the R here, but the gravitron ride in a lot of carnivals or fairs. And that's exactly what you're feeling, is a centrifugal force. You walk in on a floor, right? And then you lay against some pad, and the thing starts spinning, and it glues you to that pad. And I remember when I was a kid, I used to do just like this guy. I didn't quite stand up, I don't remember. But I definitely would crawl up and down this pad, right? Because you're supported against gravity. You're not going to fall. So you're fine. Sometimes it's a little scary, as you can see. But this is what forms our disk. So we have all the ingredients here, and I want to show you a really stunning simulation of this. So if you take all these basic ingredients, you have gas and you have dust and you have gravity. That's all you need. You don't need anything fancy. And you put it in a supercomputer, like the Starforge team did, and you let the supercomputer run. You end up with, first, it looks pretty uniform, but pretty quickly, I think it's playing. Is it playing? It might not be playing. Ah, there we go. Pretty quickly, you start seeing these filaments form, and that's that material attracting itself very, very fast. It's really efficient at doing that. Like I said, gravity is pretty relentless. And the material will start to come together, and then you start seeing these little clumps. And we don't have stars yet, but we're getting there because it's getting denser and denser and denser. And so you can start seeing even more sort of localized clusters. And this is what we see sort of broadly in space. Stars tend to form in clusters. It's pretty easy to get binary stars or even more than binary systems. And in this simulation right now, we're starting to get to the point where there are a few little stars forming. Unfortunately, it's sort of hard to tell. This is showing the density. So there's this little knot here. That's sort of a star. There's a star. There's a couple of stars up there. But I'm going to let it run for a little bit longer because then we're going to see some of the more massive stars form. And that's where stuff gets really exciting. Because a lot of these little guys, they might be a few, like similar to the mass of the sun. They're going to be like our solar system. But they don't impact their environment very much when they first form. But when you get massive stars forming, like these guys up here, do you see that big ring that expanded? That star is so bright that when it turns on, its stellar wind is really intense and it just blows all that material away. And that's how you end up with these big cavities in star forming regions, like the Orion trapezium cluster carves out a bunch of material around it and you get these big bubbles. So it's a really spectacular process. And I think it's amazing to see. But the question is, do we, I've already alluded to the idea that this is reflecting what we see in real life, but do we see it? If we go back to the image that I was showing before and we zoom in, so first off, we can already see a little bit of that kind of cavity from the massive stars in the middle there. But if we zoom into this little square here, we see a pair of stars. And those look just like those giant stars that formed earlier. And they cleared out a bunch of material around them. But I was also pointing out these little knots that are a little bit more like our sun, right? And that's actually this little guy. And this looks pretty uninteresting in this image. It's a little red guy. Maybe there's some illumination there. But if you take a powerful telescope like the Hubble Space Telescope and you point at that little red guy, you suddenly see this. And this is a baby solar system forming. And it has all the ingredients. You have a star in the middle. That's what's creating all that illumination. What's spectacular about these kinds of images to me is that these things are suspended in space, and you can see right there the disk that I was talking about, right? It formed this disk, and that disk is right where planets just like ours are going to form. And it's launching these jets, which are spectacular. Again, a lot of you probably got this picture of a similar system launching these spectacular jets from the star. And there's all this really intense stuff happening really close to the star early on. But it's still going to be able to form a system maybe like ours. Maybe it'll have an Earth around it in a few billion years. And it's just sitting there. And this is what it looks like in space. It's at that angle, just like when you look at Saturn and it has its rings, it's just suspended there. But this disk is why we see our planets in a plane, right? We see the ecliptic plane in the sky. It's what tells us that our planets formed in a disk without very much perturbation. There's not anything that really disrupted their early formation for the most part. So gravity works, and we got this disk, but now we need planets, right? We need to start actually getting some action going. So gravity is actually going to come help us again. Gravity is going to make the dust particles start to clump up. So dust particles will run into each other. They will come together just like sort of cosmic dust bunnies, and they'll start making these pebbles. And the pebbles are tiny. They're more like sort of the size of sand particles or even smaller. It's not, what you think of pebbles for the most part, but we call them pebbles because we like to abuse words in astronomy. And so so we form these pebbles and they're millimeter sized, and then they start to come together more and form centimeter sized bodies. And then eventually they reach again in special places in the disk, certain regions of the disk, they'll start to form these clumps that are able to collapse just like the star originally did. And that collapse is going to form these planetesimals. So they go from being these tiny like clumps of centimeter sized bodies to suddenly miles across. And so you get these planetesimals like Arrokoth, which was discovered by the New Horizons team recently. It's one of the furthest away Kuiper Belt objects. And Arrokoth actually illustrates for us another important stage of the planet formation process, which is that these planetesimals then will collide with each other and they stick. You can actually see Arakoth already as two of these guys that stuck together, right? So it's pretty easy to see how that can happen. They collide, they stick, and they just do that a bunch. And they can do that really efficiently. They can do that in less than a million years, maybe a few 100,000 years. And that sounds long in human time. But remember, that's less than the uncertainty with which we know the age of our solar system. So this is no time at all in astronomy terms. And you really quickly get things like the size of Mars. And these are what we start considering really the first seeds of planet formation. And they will eventually continue to collide to form cores. These rocky cores are going to be there. It's sort of like the proto-Earth. They're again, it's only in that first couple million years of the solar system's formation, and they are a few of them are going to be about the mass of the Earth. And when you're further out in the disk, you can actually get them to be about a few tens of times the size of the Earth, maybe 10 to 20 times the size of the Earth. And those are going to be the ones that eventually form giant planets. And as I said, when you move further out in the disk, that's where you get that. Sorry, struggling with the clicker. There we go. So what dictates the sizes of these cores and their ultimate ability to actually hold on to material and form Earth versus Jupiter versus Uranus is a lot of that is where they are in the disk. Because if you're really close into the star, there's not very much material. So you're not going to be able to accrete very much to begin with. And a lot of the stuff is moving a lot faster because when you're closer to the star, you have to move faster to fight off its gravity. So when you're close to the star, everything's moving faster. So it's a lot harder to collide and stick. It's a lot easier to collide and break up. So you generally are not going to form things that are too massive. When you're further out, there's a lot of things, and I can elaborate on that in the Q&A. There's a lot of things that make it easier to form more massive cores. So you can easily get cores that are 10 to 20 times the mass of Earth, and thus can accrete a lot of material and form planets. The other important part of this, is that the exact mass of the cores will dictate how much gas you can accrete from the disk, because the disk is not just dust. It's actually, the mass of the disk is about 1% dust and 199% gas. And that 99% of gas is what's going to help contribute to forming your Jupiters and your Saturns and your Uranuses and your Neptunes. If you're a core that's about 10 to 20 times the mass of Earth, you're able to reach this state where you can accrete material, you can accrete the gas in the disk fast enough to get to sort of a runaway mass. And when you get to that runaway mass, which is a little bit less than the mass of Saturn, you can then very rapidly grab up all the gas in your sphere of influence, in your sort of radius of influence in that disk. And that lets you pretty much immediately become Jupiter mass or Saturn mass. If you're a little bit further out in the disk and you're a little bit less massive, then you're only about 10 times the mass of Earth. Then you can't get to that runaway stage. So you're sort of, you can still pull in gas and it'll stick to you and it's okay, but it's not going to be nearly as fast as with Jupiter formation or Saturn formation. So you're stuck only getting up to about 15 to 20 times or the mass of Earth in total. So you sort of double your mass. You don't quite get up to that the huge, like, Jupiter's 300 times as massive as Earth. You don't get there. And if you're a lowly Earth mass planet, you can't accrete hardly anything at all. You can sort of pull in some gas, but you're not even going to do that great a job at holding on to it. So you're not actually going to build up this massive envelope around you of hydrogen and helium, even as efficiently as Uranus and Neptune do. And so you just end up mostly rocky. And that's how you get your terrestrial planets. So moving on, we've set up our system, right? We have some gas giants that we can start forming with these more massive cores further out. We have rocky planets that are forming close into the star. And then when you're about 10 million years into the life of the solar system, your gas is going to dissipate. So your gas is gone and you're left with your protoplanets. And after that, we get into the era of collisions. And because the gas is dissipated, it no longer dominates the dynamics between the planets. And actually, the planets are just left to run into each other and interact gravitationally. And the planet-planet interactions are what's going to dominate the evolution of the solar system for the next few hundred million to few billion years. So I'm gonna focus on these interactions and talk about some of the things that we see in our solar system as evidence of these collisions having happened. To give you an illustration of how these collisions happen, I'm going to show a nice simulation for a different planetary system. This is the Upsilon Andromeda system. And that system basically has one planet close to the star orbiting in a very circular orbit that's pretty fast. And then one star that orbits in a very, what's called eccentric orbit. It's a very lopsided orbit where the planet gets very close to the star and then very far from the star. And the question is, how did it get there? And the theory is that it began actually as a 3-planet system, and 2 of those planets had a pretty cataclysmic interaction where one got kicked out and one got left with a lopsided orbit. So let's watch that happen. And the simulation is going to sort of rotate around the planet. The simulation is going to sort of rotate around the system, so bear with that. But you'll see the actual collision happen. So you start out with these 2 planets. Like I said, they're in sort of relatively circular orbits, but as they move around the star, they occasionally come sort of close to each other and close to each other's orbits, right? And here's where stuff really starts to get nasty, because then they're intersecting each other's orbits, and finally you get that one collision, you get the kick out, and you're left with one lopsided orbit, one circular orbit. So the same kind of stuff happened in our own solar system. And it's been used as an explanation for potentially how the hypothesized planet 9 might exist. But it's also generally believed to be a picture for how our planets came to be in their orientation, regardless of whether planet 9 exists or not. The idea is when our giant planets formed in the outer solar system, we actually might have had a 5th giant planet, because planet formation is actually really efficient. It can be you can pretty rapidly form things that are pretty massive. So you get a 5th giant planet, and the planets were originally in these pretty compact orbits. What you're not seeing here is the inner solar system. So the innermost planet in this cartoon on the left is Jupiter. And we have Jupiter, Saturn, New Guy, Uranus, Neptune. And what's going to happen is New Guy is going to get kicked out. And you're going to end up with a system that looks a little bit more recognizable to us, with only 4 giant planets. And what we had before is a really populated belt of planetesimals. And then that belt is much less populated. And it's a little bit more like we see the Kuiper belt today. Based on sort of our theories of how efficient planet formation should be, we would expect many more Kuiper belt objects than we see today. And this simulation is going to show you a little bit of why. So it's going to count down to the collision. And there it goes. So I'll play it a few times because it's pretty quick. But you start out 20 million years before the collision. And you have your planets, and they're going to kick each other around. And as they kick each other around, they'll eventually have this cataclysmic interaction. There goes planet 9. And you're left with this much more sparse belt of planetesimals and only 4 giant planets. In a slightly more exciting simulation, we also have the collision that kicked Uranus over onto its side. So Uranus rotates at about 90 degrees relative to its rotational axis is about 90 degrees relative to the plane of the solar system. And a reason for that could be that it had a giant impact shortly after it formed. Only a couple 100 million years after it formed, you had your proto-Uranus, and then something similar to that, like sort of a few Earth masses, maybe 10 Earth masses, crashed into it. And that collision kicked Uranus onto its side and set the stage for a few other anomalies in Uranus that we see. For instance, how rapidly it rotates. So I'm going to let the simulation play a little longer. We're on hour 6. At around hour 20, this object comes back and hits it again. So we're just going to see that one more time. But that basically, that collision really speeds up Uranus's rotation. And it has to have happened pretty early on for Uranus to still have the rings that we see around it today. You have to sort of kick it around, but still have a lot of material near it for it to then reform that material into rings. It's much more sparse than Saturn's ring system, but it's there. Oh, there it is. So there's our second collision. And then this guy sort of merges in. And the details are still being worked out. This is still a very active area of research. What was the property of the collider, its orbit? Did it stick around? And hopefully we'll one day send a probe to Uranus to actually figure some of these things out. Come on. There we go. Another important collision in the solar system's history is, of course, our own. Earth, when Earth was just a baby, crashed into its sister, Theia, and that collision is actually what formed the moon. And so this is called the moon forming impact, because we're not very creative. And this collision with Theia has some pretty spectacular simulations of its own. But basically, it's because of this same kind of chaotic interaction between these planets. As they orbit, they can easily kick each other around, and then they can end up in the same orbit, and then you get this collision. And that collision pretty much destroyed, as you can see, there's no Theia left. It pretty much destroyed Theia. And it resulted in the moon, and it's part of why the moon has such similar composition to Earth. And so it's similar to the Uranus thing. You never just have the one collision. You kind of revisit it a few times. And eventually you're left with this nice Earth and moon system. It's pretty spectacular. It's always fun to see these simulations. But I'm going to move on for the sake of time. I can always come back to it if people want to stare at it. But okay, I mean, I'm pretty happy with what we have so far. We explained how we end up with a couple of gas giants. We have our ice giants because they just weren't big enough to be gas giants. We have our 2 Earth-sized planets, which I didn't go too much into the detail of, but basically, like I said, you get these planetesimals that are about the mass of Earth, and it's pretty easy to imagine how they would sort of run into each other. You get Theia, you get Moon, and stuff like that. And then you get these kind of leftovers. Mars is 1/10 the size of Earth. Mercury is 1/20. Why not? And then you get this Kuiper belt of leftovers, and it's even a little bit more sparse than you expect it to be because the giant planets were kicking each other around, and all the asteroids and comets got caught up in the action. But does this generalize? It sounds like I'm painting a pretty finely tuned picture, and I've tried to be general. And the reason I've tried to be general is because we want to explain the 5,900 other planetary systems, planets we've discovered to date. The solar system appears to be at least 1 in 6,000, or Earth is 1 in 6,000. The solar system is 1 in a couple thousand. So you can't just make a planetary model that forms our solar system by itself and can't explain anything else, right? So through these same ingredients that I've pulled together, let us build another planetary system. So when you look at the planets that we've discovered so far in this graph that I'm showing you, where in the vertical axis you have the mass of the planet relative to Jupiter, and in the horizontal axis you have the distance of the planet from its host star, we can compare how our solar system looks relative to the planets we've discovered. And there's some important things I want to point out. The first is that you notice that we've discovered some things that are a little like Jupiter, and that's awesome. That's actually been a relatively recent development based on a lot of patience from exoplanet hunters in the last 20 years, actually. We don't really have anything else that looks anything like our solar system. No Mercuries or Marses by a long shot. There's not really a Venus or Earth twin. There's like that little lonely guy. Maybe it looks like Earth. It's probably not around a sun-like star, though. You don't have anything that looks like Uranus or Neptune. So we don't see planetary systems that look like ours. What do we see? Well, we see these compact multi-planet systems. And, sorry, there should be a circle. Good, thank you. So we see these compact multi-planet systems. And I say they're compact because they're very close to their star. Notice again, this is Mercury. And these are a bunch of planets that are more massive than Earth. So you have a bunch of planets that are 3 to sort of 10 times the mass of Earth that are they're closer to their star than Mercury is to our sun. That's pretty wild. That's pretty extreme. We don't see anything like that in our solar system at all. And you might think this is observational bias. And when I put it on this plot, this is just a plot that doesn't account for any of our ability to detect these things. So some of these guys, because of the way that we hunt for exoplanets, these guys are easier to detect. That's fair. But there's a lot of people who have put work into figuring out how hard it is to find planets that are not like these guys. And it turns out that these super Earth or mini Neptune, and I can talk about what those names mean a little bit later, but basically planets that are about several times the mass of Earth and either have rocky atmospheres or gaseous atmospheres and are closer to their planet than to their star than Mercury is, are about 30 to 50% of planets. These guys are extremely common. We don't see them in our solar system. We don't see anything even close to that in our solar system. So can we form that? And the answer is actually yes. And that's because when you form planets like Venus and Earth, and it's actually pretty easy to form things that are a little bit more massive than Venus and Earth, just via this process I already talked about where planetesimals come together, they experience headwind from the gas in the disk. And that headwind is going to slow them down. And when the planets slow down, they're going to move closer to their star. And that slowdown and moving closer to their star is going to just happen sort of regardless. And the only thing that stops it is the fact that the disk sort of runs out once the star is, so when you're close enough to the star that all the dust is getting evaporated away. And that's at about like 0.1, 0.05 AU. So very close to the star. Besides that, you can move in pretty easily. In fact, maybe even our own solar system had planets like this before, and for some reason they got kicked out. They collided with something and maybe proto-Venus and got kicked out, or something happened to move these guys out. There's a lot of work being done to really understand how we go from planetary systems like this, which are formed very frequently, and models and the planet formation simulations form these very easily. It's a little harder to actually get Venus and Earth as far out as they are. Another extreme system is the hot Jupiter, which is these planets here that are as massive as Jupiter, or up to about 10 times as massive as Jupiter, and also closer to their star than Mercury is to the sun. So you can imagine how unbelievable it would be to have, instead of Mercury, Jupiter right there. And that would probably be pretty disruptive to our lives because it would have probably kicked Earth out. And this is pretty fun to look at these guys, because this is actually an illustration to scale. This is actually, if you had a star that was this big in pixels, and you had a Jupiter, this is actually how far apart they would be, which is like, this is one of the only planetary systems where you can actually do this. They orbit their stars every 2 to 10 days. So that's a very short year. You get pretty old pretty fast. And they have temperatures of 1,500 Kelvin, which is the temperature of magma. So it's a hot summer. And the question you might ask is, how do you even get those? I mean, that's so extreme. Surely you disrupt the planetary system. I was talking about migration before. Can you even migrate something in that fast? And we still actually don't really know. But it seems there's two kind of pathways to do it. One, like I said before, you get, we call it sort of the early arrival. And that's, you form Jupiter where it should have formed. And then it just migrates it just sprints toward the star, like just dead out sprints, and gets there within like 10 million years, because it needs to get there before the gas is gone, because the gas is giving you drag to move in. It's a little more subtle than that. It's actually not technically drag in the case of a Jupiter mass planet, but basically you sprint toward the star and you get there soon and you're fine. Cool. Okay, you get a hot Jupiter. We have some issues with that, but why not? And then the other idea is that you can move in much more slowly. And the way you do that is you start out at the position where Jupiter formed, and then maybe a star flies by and kicks you. And similar to those planet-planet interactions, you get a star-planet interaction. It kicks you really close to the star, and then you end up in this really tight orbit near your host star. And that's how you get a hot Jupiter. And it turns out that might be actually the favored model. But again, that this is still very hotly debated. So we're done, right? We've answered all the questions there are. Obviously, that's not true. I've alluded to many things that I haven't gotten into the details of. But there's a few really big open questions still that I like to think about, and I think as a scientific community, we're still really we really need to work toward understanding. One is what actually determines the composition. So I stopped the discussion of our solar system. I declared our solar system formed when it was like 200 million, maybe 500 million years old. There's still 4 billion years of evolution there, right? There's how do you get life on Earth? How do you get a nitrogen, oxygen rich atmosphere here? How do you get Venus with an atmosphere that's 700 times more dense than ours, but the same mass planet and even closer to the sun? So there's a lot of open questions in exactly how you end up with the planets as we see them today with their compositions. There's also the question of exactly when planets form. Remember, we don't know exactly the formation date of our solar system to within about 1 million years, and that's really good. But also, 1 million years is, like I said earlier, when all the action is happening. So we don't actually know exactly when planets form, and that's something that we're still researching. Other questions include, are there other solar system twins? The plot I showed you before of planetary systems we've discovered show that we've never seen anything actually like our solar system, with 4 terrestrial planets at those distances and 4 giant planets as far away from their stars they are. And we've never seen an Earth-like planet around a sun-like star. And that's really what we're after, right? That's what a lot of people are really excited to see. Can we find Earth 2.0? And we haven't seen it yet. And I think we're really just around the corner from the technology to get there. There's a lot of current instruments that are this close to that precision, and we just need to do a little bit better. And I think the next generation of instruments will get us there. So what's this next generation of instruments that's going to illuminate the star formation picture for us? We have the Roman and Rubin observatories. Roman Space Observatory is going to give us a survey in the infrared of especially the galactic plane where there's a lot of stars. So we're hoping to see especially a lot of runaway planets. That'll tell us how efficient planet formation is, because if you can afford to kick away planets, then that means you're way overproducing them, and that's great. Rubin Observatory is going to tell us about how many things are actually in our solar system. It's going to help us understand the true population, or better understand the true population of asteroids and comets, and it'll place some nice constraints on where Planet 9 could actually be if it's there. We're going to have the European Extremely Large Telescope and TMT hopefully soon, and both of these will be capable of getting very close to that Earth-like planet around a sun-like star. They're going to be, and they're going to open all kinds of new interesting pathways for investigating star formation. There's the next generation VLA and the Atacama Large Millimeter Arrays upgrades that are coming up soon. And these two are going to really help tell us about the distribution of gas and dust around these disks where the baby solar systems are forming. They're really going to tell us about the ingredients of planet formation, the efficiency of planet formation, and what's really going on in that first 1 million years where we still have a lot of uncertainty. And then there's the Habitable Worlds Observatory, which I am assured by people is intended to get to that Earth-like planet around a sun-like star with this advanced star shade technology that will be able to block out bright stars and really get to the precision that you need to see the very, very faint Earth-like planets around these stars that we really think should be there. So let's find them. And with that, I'll open up to questions. Thank you.
We'll just take a couple of questions before we kind of adjourn, and then we'll start our Q&A panel and open up the telescope. So just a couple really quick questions.
It's not really a question, but to help me go to sleep for like the past 5 years, I've been watching these televised lectures. So I just wanted to say, like, it's so nice to like finally see these lectures. So
That's great. Thank you. I planted him in the audience here. Yeah. Here. Thank you. That's very kind.
So for stellar bodies like Pluto, is it just kind of decided that they have like this oblique orbit just from being knocked by something?
Yeah. Basically, the idea is that they're in this ring. So these Kuiper belt objects tend to have pretty eccentric orbits, and part of that is because they're just constantly interacting with things that are similar mass to them, and they're just not that big. So it's pretty easy for them to get kicked around. And early in their formation, they got kicked around by Uranus and Neptune as well. So they're just always getting pushed around because they're not very massive. Yes. So yeah. So basically, when you have this gas disk, the question was, are there? We see other solar systems, other exoplanet systems with eccentric orbits as well. Are they because of these interactions between the planets? And the answer is yes. Basically, and they could be actually also because of interactions with passing stars. The stellar cluster, the birth cluster, where the star formed, tends to be much denser than we see, for instance, the stars around us today. And that means that it's really easy to get a star to fly by and maybe kick one of your giant planets. So usually you do need some kind of interaction like that to get this type of eccentricity. It's disks and formation in the disk tends to form very circular orbits. So then you need, once the disk goes away, you can start perturbing things.
Okay, in interests of time, because it's already 9 o'clock, don't worry. If you have questions, stick around for our Q&A panel. We're going to take all the questions that you guys can throw at us, but let's thank our speaker once more. So now is the part of the night where it's a choose your own adventure. We've got telescopes set up outside. You can go follow the signs to the fields right behind me. And for the next hour, we will be in here answering questions for our Q&A panel. So if you have questions, you can go out, look at the telescopes, come back in, ask a question, whatever you want. We'll be here until 10 o'clock. Oh, no worries. Good to see you, dude. Catch you next week. Hi. Whole 2 hours is so you can check that.
Hey, yeah. Yeah, I was just wondering, like on the graph, as you saw on the graph, it's like there's three main clusters of exoplanets. How come our solar system is so unique compared to like the other
Part of
clusters?
it is because we are not sensitive to we aren't sensitive or Mercury or Venus.
Oh, okay.
If we detected it, if it were in another solar system. So we're working on it. But part of the concentrations in that are real. We don't yet understand. But ask that question of our panel.
All right, thanks.
No problem. And it's pretty easy to look me up on. I don't send this to you. You don't get the email. Feel free to reach out. You're very welcome.
Although I did get really tired in the morning.
I went and touched it. So.
I was gonna ask, so like, what's the like astronomer's version? Like, what's your like early your go-to like supplemental for basically like planet formation, orbit,
And we're about to start the Q&A, so I should sit down.
Okay, thanks for your patience, everybody. Sorry we only got to 2 questions during the first Q&A, but now we've got an hour of Q&A, and so you can expound upon all of your various questions. So before we get started with the question, We're going to run through, and each of us will introduce ourselves and say a little bit about the science that we work on. We're happy to take questions on whatever topics related to space and astronomy and science. I'm not going to ask political questions or trivial pursuit questions. But before we get there, we'll just introduce who we are and the sort of science that we work on, so you know where our knowledge base is. So I'm Cameron Hummels. I'm a research scientist here. My research is primarily on galaxies and running supercomputing simulations to follow the formation and the evolution of galaxies, particularly the dynamics, how they evolve over long periods of time, and the regions around the galaxies known as the kind of the galactic atmospheres, trying to understand those, because we still don't fully understand the physical processes that dominate why some galaxies form into galaxies like our own Milky Way, kind of a spiral structure, and other galaxies turn into more elliptical, kind of oblong spherical structures. So, yeah.
So hi everyone, I'm Miles Sherman. I'm a grad student here, and I mainly work on, or I like to observe things that stars leave behind. So especially these massive stars, at the end of their lives, they'll explode and expel much of the material and leave behind these really dense cores. Some of them collapse into black holes, but others are leave behind are these really magnetic cores called neutron stars. And they're some of the most energetic objects in the universe. So I study the radio and other wave emission properties of these objects.
I'm Adolfo Carvalho. You all know me at this point, but I study more of my focus is on observations of how stars and planets form. So I use observations all the way from the far ultraviolet to radio wavelengths to understand that earliest first million to 10 million years of the baby solar system, and trying to get at exactly how planets form and how we get the diversity of planets we see today.
And I'm Emily. I'm a grad student here at Caltech, and I study the largest and most energetic events in the universe. So these events are collisions between massive clusters of galaxies. And because they're so energetic, collisions between galaxy clusters emit radiation all across the electromagnetic spectrum. So I get to use telescopes all across the electromagnetic spectrum, from radio waves through optical light up to X-rays, and then compare those observations to computer simulations in order to study sort of the growth and evolution of the larger structures in the universe.
Okay, so now we open it up to you guys, and I know there are already a couple of people who are waiting in line to ask our speaker a question, so I'll get to, you have a question, sir? I'll get to them first, and then we'll also take questions from our YouTube audience.
Okay, thank you. So I don't understand this completely, but the elements below iron are formed in the sun. The elements that are heavier than iron are formed in supernova, maybe. I'm not sure about that. Like, I guess my question is, though, if you were to do a distribution of the heavier elements, say like the rare earths, and you were just to give this whole talk all over again from the perspective of those heavier than iron elements, what would the talk be like, or how would it differ?
That's a really good question. Those are essentially locked into the dust grains for the most part. So those are going to form pretty rapidly into these, even things heavier than helium, actually, in the astronomical picture, are called metals. And so we really abuse the chemical side of things a lot of the time. When I was talking about a lot of the gas in that protoplanetary disk that was driving a lot of the action, that gas is dominated by hydrogen and helium. It's about 70% hydrogen. It's like 28% helium. And then it's pretty much 2%, I think, everything else. And so that everything else becomes even more sparse when you go to things like that are heavier than iron, because those don't even form in stars like the sun. Those have to form, as you said, via supernovae. And so, and even more exotic astrophysical events like neutron star mergers. So those are pretty immediately locked up in what we call solids. So basically anything that's like a couple of dust grain size objects, and they pretty much immediately go into those cores that I was talking about. So they're present in the picture of planet formation in the sense that they make up those cores, but they're not driving much of the dynamics, and they don't play much of a role, except that they contribute to heating of these bodies by radiation as the like rate when you have radioactive isotopes of them, like uranium, like potassium. I know potassium is lighter than iron, but they will decay and those heat these early bodies. But that's sort of they're always locked in the solids. Is this short answer, I guess?
I tried to draw a really crummy periodic table, a periodic table of the elements. So as the audience member was asking, iron for the most part, and Adolfo was talking a bit about this. Iron for the most part forms in stars. Things lower to the left and above iron forms in stars, and then the heavier elements tend to form in more exotic things like during supernovae or even later evolutionary stages of stars like neutron stars and that sort of thing. But you covered the rest of it, so I didn't need to make my
Sorry.
illustration. No. You did a much better job. There was obviously lots more questions. We'll get to all of them. You were also waiting beforehand, so I'll pass it to you.
Hello. So I know that Earth has a pretty circular orbit, like very low eccentricity. So when proto-Earth and Theia smash into each other, how was the outcome orbit like so circular and nice?
That's a good question. So this is where we get a little bit beyond my expertise and the detailed dynamics, but you don't need to have very eccentric orbits to get these collisions. There were a lot of things in that early inner solar system. And so they can be relatively circular orbits to begin with, and then they collide. And because they actually collide, you don't get this gravitational collision where they're kicking each other. If you get the actual physical collision, then you don't really excite the orbit into a higher eccentricity. My understanding of the dynamics is that when you get that actual collision, they just sort of stay in a pretty similar orbit to the original orbits of the two.
And over time, as the system relaxes, it wants to be as circular as possible. So it'll settle into that over a longish time scale. And since it's been around for a very long period of time,
it orbited the sun another 4 billion years after that. So there was a lot of time for it to relax, as Cameron said.
Additional questions?
So you mentioned in the presentation that we think that the Earth at least is like 1 in 6,000, I believe the number is. So how exactly do we get estimates like that? Since we are not too good at detecting Earth analogs, is this from simulations, or are we doing some kind of other observational limitations?
The 1 in 6,000 was sort of being cheeky, to be honest, because we've found about 5,900 other planets. So by definition, Earth is 1 in 6,000 in that sense. It could be rarer. There are two ways to try to understand this. One is there's a lot of work that people do to basically model first off, you can model the planet formation picture. So you take all of these details that I was talking through and you put them into a supercomputer and you let that supercomputer evolve the system. And you just see how many Earth-like planets you produce in that time. And there's different criteria you can use, but the most simple one would be a planet that's about the mass of Earth, 1 AU from its star. And you just see how many of those you get. And those, I think, are pretty easy to form pretty quickly. The more detailed question is, do you keep them after all these chaotic interactions that we've already talked about in a couple of the questions? And on the observational side, what we can do is say, well, I know the defects, I know the faults in my search method right now. I know what I'm most sensitive to and what I'm least sensitive to. So what I can do is inject the signal that I think an Earth-like planet around a sun-like star would produce via my detection method. Inject that into real data that I have, and then see if I recover it. Do I detect it? And that kind of detection, that's called an injection test, injection recovery test. And that kind of test is what actually gives us some of those statistics. For instance, it's what tells us that, like I said, it seems like about 30 to 50% of planets around stars are those close in super Earth, mini Neptune type systems, because we account for our biases in that way. What's difficult to really know is because Earth is so far away from all the other population, and right now we inject it and we don't recover it. We know already that we are not sensitive to Earth. So our true statistics on Earth are essentially, we can't find it right now. So we don't truly know how rare it is on the observational side.
Okay, additional questions?
Hi, Adolfo. Thank you for the lecture. I'm very interested in what you had mentioned about the hot Jupiters and mini Neptunes. I'm wondering how come our solar system is an exception to that commonality? And then furthermore, you had mentioned that had our solar system been a hot Jupiter, had a hot Jupiter, Earth would not look like what it would look like today. I'm curious if like this exception that has appeared in our solar system has allowed for conditions of a more stable planet suitable for life, and whether that might be a reason why we might not find such conditions elsewhere in the galaxy or in the universe.
Yeah, that's a very multifaceted question. So the issue of how exotic these other systems appear to be is what I said a little bit before about especially how common they are, right? So our solar system does seem to be exceptional. Our understanding of how exceptional is extremely incomplete because, as I said, we, for instance, cannot currently find Earth around a sun-like star. But that said, what that has prompted is a lot of interest in the ability to create life or sustain life on planets that are more exotic. You know, can you be pretty close to your star and still actually host life and end up with an Earth-like biosphere, even though you don't actually look anything like our solar system? So the challenge, for instance, to the hot Jupiter picture is that we have actually found planetary systems where you have a hot Jupiter and then you have a sort of Earth-like or Earth mass or several Earth mass planet exterior to that hot Jupiter. Now, the issue is if you have the rapid migration picture that I was talking about, where Jupiter forms and then books it toward the star, it's going to shove all the other planets out of the way, right? It's going to kick everything on its way in. And so there's no way, or maybe not no way, but it's really hard to keep these planets exterior to that hot Jupiter's orbit. But we observe them. So how can they form? How can hot Jupiters form in that picture? And the answer maybe is that that's not a universal model for hot Jupiter formation. And so there's, in the broader picture of planet formation, I think there's these two sides where you want to figure out exactly how our solar system formed. But if our solar system is super rare, and remember all the action that I talked about today happened in that first maybe 500 million years of formation, and you have 4 billion years of dynamics and giant planets kicking things around, and there's comets that I didn't even talk about, and there's even more interaction in the inner solar system, then maybe having a general picture of how all of these other planetary systems form teaches us the rules for planet formation and the timing and all those important pieces. And then it's maybe not that hard to get 1 in a million to look like the solar system, or maybe 1 in a billion. And again, because we don't know the true rarity of our solar system observationally, it's hard to give a more concrete answer than that.
Oh, so many questions.
Thank you so much for your talk. My question was in those early stages of the star formation, when you were talking about the dust kind of colliding together and making these so-called mini stars. I was wondering whether there were any temperature fluxes in that process and if that would have an effect on the creation of a solar system.
So yeah, there's, as far as we understand it, it appears that planet formation is a hot process. So that it's not so much that initial collapse that is necessarily that hot, but because it's so small scale, but these collisions where the planetesimals are coming together and forming the cores, and then eventually the core accreting the gas, seems to be that if you have a Jupiter mass planet forming, it can be a thousand, maybe 2,000, maybe even 3,000 Kelvin. And that's something that is being very actively investigated today via a lot of mainly supercomputer simulations to understand what those conditions are around those very young Jupiters. We have some observations of them that indicate, of young planets that indicate they should be pretty hot. But we don't know exactly how hot, and that's because we're looking through a lot of gas and dust in the disk still, and that obscures our line of sight to really study that physics near the protoplanet. But it should actually be pretty hot, and that poses a challenge to things like we know that ices in the solar system can have pretty complex molecules that we call organics, molecules that could even have some of the building blocks of life. But when you get things that hot, you can't actually deposit those molecules into that planet because they'll just be destroyed. And the ices will be liberated into the disk and they'll circulate up and you lose them. You don't actually come into the planet. So that actually does pose a problem for depositing that material into the planet. There's other, like the Earth-Theia collision was actually also probably pretty hot, and the temperature in that collision could have reached thousands of Kelvin. The Earth was definitely molten as a result of that collision. So that sort of also resets anything you might have been doing if you were actually doing any kind of geophysical stratification and forming a crust or anything like that. That gets reset by that really hot collision, and you just turn into a ball of magma again. So the formation process seems to be a really hot one. And that definitely is going to impact exactly how and when you can get certain materials to your planet.
I'm going to ask one of the questions from our YouTube audience before we go back to our in-person audience. And, you talked about the protoplanetary cloud, the protoplanetary disk, and how the grains of the dust eventually accumulate into larger and larger clumps that eventually form the kind of the seeds of planets. So the question is, sand on ocean beaches has existed for millions of years, and we don't see those build up into larger structures due to gravitational interactions. What's different, the sand on planets compared to the dust in these planetary disks?
The most simple answer to that is just that the sand on beaches is not isolated. And in fact, the grains that come together and stick in interstellar space, the reason they stick isn't strictly gravity. It's a little bit more subtle than that. And so it has to do with electrostatic forces and what the exact charges of the grains are and their precise material properties. And so when they come together and stick, it's more because they're sitting in the not really vacuum of space, because it's actually a pretty dense environment in this early stage relative to like our solar system today. But they're sitting very isolated. It's definitely a vacuum relative to like what we have on Earth. And so they're just kind of floating around in this relative nothing, and then they bump into each other, and then they'll come together and they stick. And if you do that with sand grains on Earth, they still do sort of stick a little bit. But the issue is there's a lot of other stuff. There's air, there's water, they have if they're metals, they might have oxidation around them. And so there's all these things that prevent things. There's all these, there are other forces and sort of contamination sources on planets that are going to impact the ability of these things to stick together. But for instance, if you take metal, if you take raw like iron and you sand it, or you file it so that it's exposed and it's not oxidized, and you take it up into space and you touch two pieces of non-oxidized iron to each other in space, they will actually just weld together. And that's because the iron is totally exposed. And when iron is on Earth, even though it's not visibly rusty, there is an oxidation layer that prevents that from our oxygen-rich atmosphere. So when you're in space, the environment is just so different that it's conducive to different types of sticking interactions. It's actually, it takes $1 million laboratories on Earth to simulate astrophysical environments that teach us exactly how sticky dust grains of different compositions and of different sizes are in space in the early solar system environment.
Yeah, maybe just sort of stepping back from that, I think that question raises a really important point that Adolfo was alluding to, which is this idea of environment in the universe, and particularly the fact that things don't tend to grow in isolation in the universe. And so much like, dust grains will behave differently versus when they're on a beach, or sand grains on a beach versus when they're floating in space in a proto-solar system. Another example I can think, sort of zooming out, is galaxies. So when we look at galaxies across the universe, they can look very different from place to place. In particular, I would think of galaxies and galaxy clusters can look very different from galaxies and only smaller groups of galaxies. This happens because as you fall into a galaxy cluster, a galaxy can have a lot of its gas sort of stripped away. It can undergo lots of really fun interactions. We've got several talks on our YouTube channel about these sorts of interactions before. And then you end up with a population of galaxies in your big cluster that looks very different from, a single galaxy that might exist elsewhere in the universe. So just things to keep in mind as we think of objects in the universe, whether they be as small as, sand grains or as big as galaxies, the environment really, really matters. And sort of contextualizing our objects sort of in their global environment is super important as astronomers.
The one thing that I'll add is we do see clumping of sands on the Earth for different reasons, but you see sandstone. Sandstone is aggregated sand that is due to the processes around it, both erosion processes, wind, water, and so on and so forth, as well as the chemical things, causes these sand grains to clump. But it's kind of a different environment, and you have different disruptive and kind of accumulating forces than you do in space, but it is a similar kind of process. Okay. I'll get you guys in a second.
Hi, I was just wondering if you had like 10,000 astronomers right here, would they all agree with everything that's being said and theorized? Because it seems like such a tough science, thinking about things billions of years ago. So I feel like, would you all disagree, or do you kind of talk to each other to make sure you don't send out the wrong facts sometimes?
That's an excellent question. And I don't think it just applies to astronomy. This applies to science as a whole. It's hard. I'm not going to brag that it's the toughest, but it's one of the hardest sciences, I think, to do. But yeah, I'm sure we all have opinions that then we can respond to your question in turn. But I would say there are general consensuses that are made by the astronomical science community where there's agreement on basic facts. And these are led to things like general acceptance of the laws of gravity, or general relativity to describe the space-time of the universe, or quantum mechanics as a very good descriptor of things on small scales. And the reason that everyone agrees on this is because we have experiments that we test these theories or paradigms have tests that you can make predictions. We can test those predictions and either verify that the model is correct or challenge that the model is incorrect. And thus far, quantum mechanics or relativity have succeeded in making the correct predictions that are verified with experiment. But there are other areas of the field where there is some sort of controversy, where Adolfo and I might disagree, or Miles and I might disagree about a different topic. And those are on the very edge of what we understand. And oftentimes the most exciting things in the field are the things where there's some controversies. But I think largely the things that Adolfo was talking about in his presentation are generally accepted at this stage. And I think you pointed out some areas that were on the edge that we don't yet have answers about. But yeah, please.
And just to add to that, so some of the controversial opinions, or like the more out there results, sometimes those are the things that can spur on the newest science. I mean, I think one of the most interesting examples, to me at least, is the prediction of gravitational waves. These are basically ripples in space-time itself. And when they were proposed, that's seen as this very wild theory from general relativity, that you don't really, it's like, how can we even prove that? And now today we have the LIGO detectors that are detecting gravitational waves every day, every week. So it's important to have some of those cognitive dissonance in order to spur on the new results and new ideas. Yeah.
Yeah, I guess I'll just add quickly. One of the cool things about astronomy is that it's a very sort of global science, both in the Earth-wide sense, but also the fact that we have lots of astronomers all over Earth coming at the questions that we're asking from very, very different perspectives, and then sort of collaborating to find underlying truths. And so I think it's really cool that if we have one of these interesting questions, like if we want to detect gravitational waves, we can have people from all over the world come at these questions from very different perspectives, maybe developing unique techniques, and then sort of testing their hypotheses together and seeing if we converge on one solution, or if we can learn something about not only the object or the question that we're trying to ask, but about our own methods, about how well we can model things. That has applications for all other fields of science as well as astronomy. And so I just think that's one thing that's really cool, is just this community of global scientists coming at things from very different perspectives. And yeah, just learning a lot along the way.
I will say I tried to stay very well within safe territory on this talk in terms of my understanding of the agreement in this planet formation community on a lot of things. But there are some things that I talked about today that people could get upset about. There's the one example might be the importance of forming Mercury and Mars. And so I sort of jokingly called them leftovers. And that's because in a lot of planet formation models, it's, like I said, very easy and quick to form things that are about the mass of Earth, pretty close to their star. So you just end up with a bunch of things, and why not end up with Mars and Mercury left over in the end? But in more detailed models that try to form our solar system, it's actually really hard to do. And we still don't have a good understanding of exactly how you form Mars or exactly how you form Mercury. It's actually quite a huge open question in the formation of our solar system. There's all kinds of other things. That's part of the importance of conferences and why we attend them, is to have conversations about these kind of cutting edge things that we're seeing and have arguments. I mean, there's people do usually during the Q&A. It's not that often that somebody interrupts the talk, but people will say like, no, that's not correct, I disagree, or like, there's actually sometimes disagreement in the planet formation community compared with people who focus on the solar system, where there's a planet formation model that is a little bit more like the broad strokes kinds of things I was talking about, that they say like, okay, well, we get these giant planets and we get these terrestrial planets, and it generally explains things well. So my model's pretty good. And then somebody says, no, your model's trash because you're not explaining this class of asteroids that we see in the solar system, and you can't possibly explain it because of these your initial conditions. And there's all, you get these arguments like this, and they're really good for moving science forward because
and it can get heated.
Critiqued. I mean, you're a theorist. You must get this kind of
stuff. Yeah. It can get really heated. It doesn't usually turn to fisticuffs, but it can get pretty heated.
Yeah. And that's sort of the beauty, is we're all doing our best. And usually it comes from a place of respect of, I trust that, I disagree with what you're doing and I want you to do better because I see something different in my observations, or my models are predicting something fundamentally different. And if you're going to have a model that you're saying does so well, you need to explain my stuff too. And that moves science forward. So it's important to disagree, and we frequently do.
I'll just add one more thing. It's these sorts of disagreements that have allowed us to, within the past 100 or 200 years, answer questions like, what is the sun actually made of? And is the Milky Way the edge of the universe or not? And so even in the past couple of centuries, these sort of questions and lively debates have gotten us really, really far in our understanding of the universe. So it is pretty cool.
Yeah, absolutely. Challenge and then respond, challenge, respond. I actually know one of my former colleagues, well, I guess he's still a colleague, but he's not here. Like almost got into a fight with a Nobel Prize winner about black holes about 5 years ago. He's like, come on, let's go, Genzel. And Genzel's like, calm down. So it's pretty funny. Okay, more questions.
To what extent is this process still happening in the solar system? For example, you put up the image of Arakoth, which is a contact binary, and we have pictures of that because it just happened to be in the path of New Horizons and was an interesting target for them to point that probe towards after it flew by Pluto. So I'm sure it's not alone. And I know there are other contact binaries out there. If we fast forwarded 500 million years in the life of the solar system, would we see coalescences happening in the Kuiper belt of objects into larger objects like Pluto or Charon or whatever? And then related to that, what accounts for the asteroid belt and its fragmentation? I know, as I understand it, like there's not a ton of mass there. Like Ceres represents a really large percentage of the total mass of everything there. So is it just that it's just too much stuff too dispersed, or was it something larger that fragmented into what it is now? So it's two separate but sort of related questions. Because the relation being, could there be object coalescing in the asteroid belt in the way that you can imagine happening in the Kuiper belt as these contact binaries accrete onto one another?
Sure.
No.
Yes, you can have
controversy. I'm going to say no because they're too close to Jupiter. Jupiter's
no.
gravitational field.
That was where I was.
Okay. All right.
I was headed there.
Sorry, I cut you off.
My sure was to the Kuiper belt. So the Kuiper belt's cold. Things are slow. Why not? They can collide and stick. To Cameron's point, there's the asteroid belt is a very tricky dynamical situation. Things are moving fast and they're close to Jupiter, which means Jupiter's always kicking stuff around. So a large, part of the answer so the asteroid belt also has this compositional gradient where things that are closer to the sun are sort of generally ice poor, hydrated minerals poor, and things that are further out are more ice rich and they seem to have more hydrated minerals. And that compositional gradient doesn't actually necessarily come from the real temperature gradient of the asteroid belt today, but rather from the idea that Jupiter can sort of kick bodies from the outer solar system into the asteroid belt. And so there's a lot of interaction that happens with Jupiter, and I say Jupiter especially because it just dominates everything. It's just so massive that it's really what's driving a lot of the action. And when you're that close to Jupiter, you're probably not stable enough to form a planet. Things are, again, moving pretty fast. So you're much more likely to collide and break up than collide and stick. And so we're probably not going to see like a planet form in the asteroid belt. But the reason it's relatively sparse of material is largely due to the fact that in the sort of the formation process of the terrestrial planets, in addition to the formation of Jupiter, you're just kicking stuff everywhere. Generally, in order to understand this idea of later planet formation, something that's been really exciting in the last probably 10-ish years, but honestly started with the birth of the exoplanet field, is the detection of planets around older stars and detection of planets around stars that have long since sort of died. So the pulsar planets, there were three planets that were discovered before 51 Pegasi b was discovered in 1995. those planets that were discovered, and 51 Pegasi b is a hot Jupiter around a sun-like star. So that was the famous Nobel Prize winning discovery by Michel Mayor and Didier Queloz. But before that, there were a few planets that had been discovered by the fact that you had these neutron stars that were rotating, and so they're sending pulses, and we can time those pulses very precisely. And if a planet passes in front of it, it'll block a pulse and mess it up, and so we don't get that pulse. There's other ways it can perturb the pulse, but that's a simple way to picture it. It can block the pulse, we don't see it. And so that's how you kind of see a planet. Another way is if the planet is kind of moving the star itself, and that'll change the timing of the pulses as well. And I forget exactly which of those techniques leads to the pulsar timing detection of planets. But the basic idea is you have a planet around a star that's long dead and a star that was way more massive than the sun. So how can you actually get that planet? There's theories that say that basically the star gets rid of all of its material during its late stage evolution. That material it's a lot of gas, and that gas can then cool down and form dust, and that dust forms a type of protoplanetary disk. And from there, you can actually have enough material to form a planet, because that's a lot of mass that these stars kick off in their dying stages. But there's also a lot of questions, or maybe that planet already existed there, but how did it survive the relatively violent process of a supernova that results in the formation of a neutron star? That's a really tough question to answer. So there's a lot of so that's sort of the idea of these sort of later generation planets that can form well after the planetary system is formed, planets that form well after the star itself might have even died. Is something that's a pretty new area of research, and there's all kinds of instruments that have enabled better study of these particular systems to understand exactly that much more exotic flavor of planet formation, but that could nonetheless lead to even potentially habitable planets.
I'm just going to ask a multi-part question. So, when the solar system or a star system is forming in the beginning stages, and the gas or the giants are forming, what I remember from the lecture is that there's still like the big planets or the big rocky masses, they accrete more gas because they have more gravity in its orbit and surroundings. So is that I'm formulating it in my head. So is that the only reason that the giants are where they are in relationship with distance from the sun, or does the distance itself play a role in where the gas is mostly away from the sun and where the rocky stuff is, which is closer to the sun?
So it's a little subtle because it's neither. It seems like the answer is related to where the ices are. And this is something that I didn't really have time to get into, but I'm glad you asked. So there's this thing called the water snow line that has turned out it appears to be very important to giant planet formation. This water snow line is distinct from the like liquid water habitable zone people might be familiar with. It's the water snow line is the habitable zone being where liquid water can be sustained on a planet based on the planet's distance from its star because of the temperature that planet ends up in equilibrium with the radiation of the star. The snow line, the water snow line or ice line, is basically where it's where the irradiation from the star is enough to sublimate water ice, H2O ice, from the surface of dust grains. And that's at around, I think, a couple of AU. I forget, it's like 3 AU or something in our solar system. The temperature is about 170 Kelvin. So it's much cooler than water ice on Earth because of the vacuum of space. And the basic idea is if you're closer than that, water is a gas. If you're further than that, water is ice. There's no liquid water in space. And this ice line the fact that, there's a couple of things it can dynamically do. One is that it tends to concentrate material, because if material moves interior to the ice line, the ice sublimates and it loses it. That material, the water. Sorry, sublimation is when material goes directly from ice to gas. It skips the liquid state. So on Earth, we have the three states of matter are ice, liquid, gas. I'm not going to get into exotic states. Ice, liquid, gas, right? And those are defined. Ice water is when water is colder than 32 degrees Fahrenheit. When it's hotter than that, it goes to liquid, and then at 212, it goes to gas. In space, you don't have this water stage. You go straight from ice to gas. That process is called sublimation. You see that with dry ice on Earth, where dry ice goes from like a block of dry ice immediately to gas. That's how smoke machines work, fog machines work. But basically, this snow line turns out to be important because it tends to, for a variety of reasons, it concentrates material. And there's theories that and there's some results that seem to show that maybe it even makes the grains a little stickier, which means they tend to collide and stick more than collide and break up, which means you can much more rapidly form more massive things. So this is something that we're still trying to really understand what role that plays. But what I can tell you is observationally, when you look at the population of giant planets that we observe, planets that are about Jupiter mass, a few times Jupiter's mass, they live predominantly near the snow line of their stars. And so it seems like giant planets really like forming near the snow line. And in our own solar system, there is the theory that Jupiter and Saturn formed very close to the snow line and eventually migrated out via those the giant planet dynamical interactions I was showing in that simulation. Remember, they started very compact and they end up a little more spread out. In that compact configuration, it has Jupiter forming very close to the sun's snow line. So we see it observationally. There's a preference for planets, giant planets near their star snow lines. And it's something we're still trying to understand exactly why. There's a variety of maybe reasons, but we don't quite get it yet.
And so does this mean that the giants also have rocky cores? And also, if there's a hot Jupiter, is that also a gas giant like in the other star systems, or it doesn't matter and we're just calling it a hot Jupiter because of its size and the closeness to the star?
So they started out with rocky cores, but and this is a level of planetary interiors I'm very quickly out of my depth in. But what I can say is that the rocky core it started with, in the case of Jupiter, for instance, was about 20 times the mass of the Earth. Jupiter today is about 315 times the mass of the Earth, which means it's 10 to 1 gas, or almost 20 to 1 gas, right? And that means that the gas is going to totally dominate once you accrete enough of it. And it could be that basically you crush that core, and as you get all this gas in, the gas will just incorporate the molten and evaporating core material into it. And so you have a region of the atmosphere that is a little bit more rich in these, what I called metals, essentially the non-hydrogen helium material. But it's a relatively small fraction of the mass of the planet, which in the case of gas giants is hydrogen and helium. Similarly, for hot Jupiters, they seem to be essentially the same type of composition as Jupiter's, but just very close to their sun. And this is another place of controversy that I'll say. People are actively investigating the actual composition of these giant planets, because even in the case of Jupiter, it's really hard to know what its composition looks like deeper in its atmosphere, because we're only really sensitive to the upper layers of that atmosphere, and we're really only getting sort of a grazing look at it. And the same for other exoplanets. It's very hard to study their atmospheres.
Yeah, so people describe the core of Jupiter as potentially a metallic hydrogen. And that's not to say it's a metal, it's just that you compress all that hydrogen with more and more gravity of the hydrogen that's sitting on top of it. Much like when you jump into the ocean and you swim deeper and deeper, your head hurts because you're under more of the water. So there's more pressure on you. Eventually that pressure is so substantial that it can change the phase of that hydrogen to no longer be this fluffy gaseous stuff, but more behaving like a metal, like iron, like aluminum under all of this pressure. But we don't have any direct observations of that because it's in the center of one of these dense planets, but we can probe it using other means like seismology, like when we see waves that are traveling through that, like Jupiter quakes that are traveling through that, and you can learn something about the interior by the acoustic waves and the vibrations that are going on the surface of those planets. We actually have a stargazing lecture from about 5 years ago or 4 years ago by Janusz Dewberry that's all about planet quakes. So I can give it to you afterwards, or you can search our YouTube channel. There's all sorts of information about it. Okay, we've got time for we've got like 16 questions. We've got time for like 5 minutes here, so let's do what we can. No more double dipping. No more double questions.
Oh, golly. It's fine. Hi. So to my understanding, which isn't that great, but to my understanding, space, like the way space moves is like relatively slower to Earth's time. So I was just wondering, like, as astronomers, what like your daily like work life would be, because I don't know how that would work.
Sorry, could you repeat the last bit? I just missed the last couple words.
Sorry. Like how like a daily, like how like your work day would look like.
How my work day would look in space. That's a good question.
Sadly, we're not in space. We're here on Earth doing stuff in an office setting. So it's not unlike what a lot of people's workday is like. I mean, it depends on each one of us. Some of us are observers using telescopes on the ground. So there were people who were going to be on this panel, but they couldn't be on this panel because they're actually going to be using a telescope later tonight, like the Keck telescope in Hawaii to observe. So they were like, no, I have to get some early sleep so I can stay up all night looking through the telescope. But then there are radio telescope scientists who use radio telescopes to look up in the sky, and you can use those during the daytime. Same with space telescopes, X-ray telescopes like what Emily uses. Theorists like me, we just sit on a computer and do stuff. So it doesn't matter when as part of the day. Adolfo.
Your workday might slow down because I think the microgravity messes with your brain.
The microgravity messes. Certainly something's messing with my brain. But yeah, I mean, I think your ultimate question was, does time pass at a different rate in space than it does here on Earth? Was that kind of what I was getting at? Or that wasn't your question? Okay, we can talk about that briefly. So general relativity, Einstein's big theory, one of his big theories that he contributed to science, showcases, and there is evidence of the truth of this, that time passes at a different rate when you're in different gravitational fields or when you're traveling at different speeds relative to other observers. And so, for instance, because we're here reasonably close to the Earth in the Earth's gravitational field, time passes at a slower rate than it does if we were up 1,000 miles up above the surface of the Earth. And we can measure this difference. And in fact, you have to account for this difference with how satellites and GPS satellites that are traveling overhead, that they experience time. It's not that there's something special about them. It's where they are in the universe, time passes at a different rate than it does here. And if we were even closer to a more massive object like the sun, time would pass even more slowly. But when I say slowly and fast, the difference is like nanoseconds. So it's very, very slight in a gravitational field like the Earth. But if you were very close to a more massive object like a supermassive black hole, this could be substantial. This could be like, as is portrayed in the film Interstellar, if you've seen it, spoilers, at one point, and this is factually possible, if you're close enough to a particular supermassive black hole, you might have time that passes for only an hour of your time on the planet, but it's like years of time for someone who's a substantial distance away from that supermassive black hole and that gravitational field. So this is like a real effect. It's called time dilation, and it's a real effect. But fortunately for us, we don't experience a lot of that in our everyday work. But I mean, in computer modeling, you have to account for these sorts of things depending on what you're trying to simulate. Okay, we've got like 2 more questions probably. something like that. I already got you, but I didn't get you. So.
Awesome. So thank you so much for your lecture today. So I really enjoyed the topic of the universe and black holes. If we could get, I know there's 5 minutes left, but so what I was kind of doing my own research on, like just on the side. So like the fundamental aspects of black holes are mass, angular momentum, which is spin, and also the charge, right? I was thinking, okay, similar to like the universe, it's a neutral charge. Black holes usually have a neutral charge. Mass, like the universe is huge and it's expanding. Black holes expand when they gain mass. I was like, does the universe also have a spin in a way? Like, I don't know, because is that possible to have the entire universe to have a spin?
You're basically suggesting that, are you suggesting that the universe itself has similar properties to a black hole? So maybe the universe is a black hole?
Topic right now is being talked about, like, oh, are we in a black hole? But it kind of sounds funny to say like that. Yeah, but I guess.
Well, that's okay. That's a perfectly fine question to ask. Last year when we had the stargazing lecture with Nobel laureate Kip Thorne, who has done a lot of work with black holes and is one of the fathers of the LIGO project, there was this question: is there any evidence that our universe is actually inside of a black hole? And his answer was no. So don't worry, I won't leave it there. But our universe has a lot more properties than just like black holes as we know about them. Can basically be defined, as you suggested, by 3 different properties: their mass, their spin, and their charge. And so that makes them very simple objects. I mean, if I could describe anything like that water bottle, you could say, oh, it's kind of large and it's got some crosses, some grid across it, and it's black, but it's glass. I mean, I've already said 4 things about that just poorly define this bottle, right? So black holes are very, very simple objects, but our universe is composed of all manner of different things. It's constituted by protons and electrons and neutrons and quarks and photons and all sorts of things. And it has a weird distribution of stuff that's largely defined by a cosmic web of things. Like already I've said like 6 things about the universe, and I haven't even basically begun to cover all the things. So our universe is much, much more complicated than such a simple structure as a black hole. There's probably a lot of other things we can say about it. Please, Miles.
Oh, yeah, I was just going to add a bit to that. So there are a few, in cosmology, we try to study how the universe sort of was created, how it evolves, and how it behaves. And so there are a few things that we know from that as far as trying to say if the universe has some sort of spin. So the first thing you would need for it to have a spin is an axis, right? So you'd have to have a preferred place in the universe. And we know from observations that there isn't a preferred center of the universe. And so that's one thing we can use to say at least that it's probably not rotating, or it's probably not spinning. Another thing that we can say is that the universe is expanding. So that's something we observe by the redshift of what's called the redshift of objects. So as light is traveling to us from farther objects, it's getting stretched as the universe is expanding. And so we know that things are always moving away from everything is moving away from everything else, if that makes sense. And then so there's these sort of universal properties that we were trying to understand about our universe, and they help us understand not necessarily if we're living in a black hole, but at least what is our universe, what's the nature of our universe. We're starting to try to constrain that.
Yeah, well put. And that brings us to our end of our program. Sorry we didn't get to everybody's questions. Sorry, YouTube audience, that we didn't get to all of your questions too. Thank you guys for sticking around. Let's have a round of applause for our panel and our speaker tonight. Hopefully you got an opportunity to look through the telescopes. Again, we'll be doing this in a month's time, a Spanish language event on Friday, August 15th on black holes in Spanish. Our Astronomy on Tap will be in a week and a half on Monday, August 4th on the Dragonfly mission to Titan by JPL scientist Morgan Cable, and on supernovae by a Carnegie Observatory scientist named David Vartanian. And Stay tuned for upcoming events, dark sky festivals, and so on and so forth. Have a wonderful weekend.